We're going to hear the first talk of the afternoon from Radu. He's going to be talking about higher spin field theory for classical gravitational scattering amplitudes.
Thank you very much. And I'd like to begin, as everyone, by thanking the organizers for the invitation to speak here. This is a talk based on work done and completed very recently with Zvi Bern, Anders Luna, Jiaxuan Shen, and Mao Zhang. So higher spin field theories have a long history, and despite their long history, there is no fully consistent quantum theory of such fields, with finitely many of them, including massive fields. And just to avoid being accused of holding you here on false pretenses, this unsolved problem will not be solved before the end of this talk. What we're going to talk about is the construction of a field theory that deals with the classical physics of such fields, for which there is plenty of experimental evidence. From far away, pretty much any big body will look like a point particle, and we have plenty of evidence of spinning bodies, which are big. We live on one of them. So from far away, they look like point particles, and they spin. And if you think that the spin of these guys on the screen is very low, well, all you have to do is look a little bit further out, and you find things with substantially higher spin. The reason that the field theory counterparts of these big objects with which are spinning has to be large in h bar equals to 1 unit is that, well, goes through the classical limit of quantum fields that was discussed a little bit earlier today. So I'm not going to repeat that in general, but I'm going to say just a couple of words about what happens if you have a spinning body. And you demand that that the de Broglie wavelength corresponding to its rotational momentum, 1 over m omega r, is much smaller than the size of that object. Well, all you have to do is multiply by the denominator and figure out that the intrinsic angular momentum of that particle, or body, or whatever it is, s, m_r square omega up to factors of 1/2, or so, having to do with the precise shape of that object, has to be much larger than 1. So combining this with the fact that the impact parameter from general considerations has to be also large, and the orbital angular momentum of a two-body system has to also be large, it follows that the classical limit of moving particles with spin which exchange momenta of order q has to look like this. L is of the same order as S, it's of the same order as 1 over q. This is sufficient to figure out exactly how these big bodies are supposed to scatter. And here is, there's an ingredient that goes into that, which is the fact that Newtonian potential is classical. So if you look into this, you figure out that a 4-point scattering, meaning you have a particle of spin 1 and one of spin 2 scattering into the same thing, at order g to the n, where g is Newton's constant, has a potentially classically divergent piece, meaning that it scales faster. It scales a little too strongly with the momentum transfer. And then it has a classical piece which scales in this particular limit I was describing, just like the Newton potential, including the g to the n. And the coefficient here, m index n, is a homogeneous function under such scaling, meaning that if you make q small and s large in a commensurate fashion, then you get this particular homogeneous relation. So the question is, what kind of particles do we really need to actually accommodate and describe such a scattering amplitude? Here, n a priori could be an arbitrary function of S1 and S2, just as it appeared in, for example, Justin Vine's talk this morning. So it turns out that this cannot really be accommodated, at least not easily, with particles of finite spin. The reason is an old result of Renandra-Hallen, Kriplovich, and Pomeranski independently, that, and perhaps others, that a spin s particle has only 4s plus 2 single graviton form factors. That basically means that if you were to scatter 2 of these guys of finite spin s, then you'll have here a polynomial in spins, and that polynomial will have that many terms. So if you want an arbitrary function of the spin, then that requires an arbitrarily large spin. There is also a more technical argument for this, which I'm not going to go through in detail, but it will be slightly important later on, and it involves just group theory again, and it has to do with the fact that for any matrix of finite size, if you multiply sufficiently many of them, then you end up getting things that are dependent on symmetric products of lower factors. So the relation is something like that for some CK, whose form is not important right now. The thing to notice here is that in this relation, there is a reduction in the number of Lorentz generators. Therefore, it seems like there is a reduction in the potential number of spin vectors related to the Lorentz generators by the Pauli-Lubansky vector or operator or relation. However, this needs to be treated with care. So while S is large in the classical limit, and this seems like this will reduce the number, such relations will reduce the number of spin vectors, there are these classically divergent pieces which don't appear, which could potentially compensate. So one needs to take this kind of reduction in the number of spin vectors with a little bit of care. So having said all this, there are several reasons why we might want a four-dimensional field theory to describe our big bodies which are scattering, or perhaps in the right energy regime, have a two-body bound state. So a Lagrangian, and the four-dimensional Lagrangian, provides a natural diffeomorphism invariant completion of whatever three-point interactions higher spin fields and gravitons might have. For example, an example of such things, of such three-point interaction, is the minimal amplitudes that appeared in Justin Vine's talk and also in Yutin's talk earlier today. A four-dimensional Lagrangian framework also provides a natural inclusion of additional structures that do not have three-point matrix elements, such as nonlinear form factors. That's just a fancy way of saying that you can add terms that contain Riemann square terms to the Lagrangian, and these terms will not be related to the three-point amplitudes that one uses to construct, we used to construct the Lagrangian in the first place. And also it provides a framework to directly identify multiple moments and compare them directly with gravitational, with multiple moments appearing in GR calculations. Now, this said, there are existing Lagrangian-based approaches, but they use a word-line format. They were developed and used extensively in to describe the PN expansion, and some of them that will also appear later in this talk appeared in Yutin's talk earlier today. And last but not least, a four-dimensional field theory makes contact between higher spin fields and the efficient and powerful computational techniques developed for scattering amplitudes. So we may use those to actually compute what we want, in particular effective interactions of two bodies. So the kind of Lagrangian that I'm going to aim for, and we aim for, is not one that allows higher spin fields to propagate inside loops, because that stuff is in fact a quantum mechanical effect, and we care only about the classical physics in this particular talk. So the higher spin fields are to be thought of as dynamical, or rather quasi-dynamical sources, meaning that they propagate, they are allowed to propagate, but they don't appear in closed loops. Another way to think about this Lagrangian is as a generating function of all possible form factors of a product of two such higher spin fields. Now, there is, of course, a lot of early work on amplitudes, and it would take the rest of this talk to actually review all of it. Most of the authors are, I believe, in this meeting, so I'm not going to read their names. Now, I will single out a few works which, if I speak fast enough, I'm going to end up mentioning again later on. So as Justin and Yutin showed earlier today, the scattering amplitude of two Kerr black holes has been known for some time, and it has been computed through GR methods for arbitrary number of spins, and also from a minimal three-point amplitude of two higher spins and one graviton. Then there is an early work using spin-a-half and spin-1 to compute various terms in the post-Newtonian expansion of scattering amplitude of such particles. Then there is work involving massive spinor helicity and other techniques. again, to compute to compute 4-point amplitudes of such particles. And last but not least, there is a spin-a-half calculation of the scattering of 2 particles in the heavy particle effective field here, which does contain the complete momentum dependence. So one might call this the second order in the post-Minkowskian expansion of the scattering amplitude of 2 such particles. So after this introduction, the plan for the remaining of the talk is to talk a little bit about kinematics and a little bit more about classical limits. That means how we're going to describe the asymptotic states, and then show you the action, show you some properties of the action, talk a little bit about scattering of compact objects at order G with arbitrary multiple moments, and then talk a little bit about one loop scattering amplitudes to bilinear order in spin. And that's really just, in principle, this is just a simplification, if you wish. The formalism should, in principle, allow us to compute arbitrary orders in spin and close with some conclusion and outlook. So how are higher spin fields typically described in field theory? Well, they are given typically by symmetric, traceless, and transverse rank S tensors. So this refers to a field of spin S. And their corresponding polarization tensors are symmetric, traceless, and transverse. There is little to be said about the first two, but the third one has a very specific meaning. Well, actually, the first two guarantee that we're talking about the representation of the Lorentz group. The third relation is needed if one wants to project out of this things which are not in a representation of spin S of the little group. However, for the purpose of identifying a classical spin vector, this projection is not entirely relevant because the spin vector is a continuous quantity as a classical object. The only thing that we care about really is a magnitude, which we are going to call S, but it doesn't really need to be correlated with the spin of the quantum field. And also a direction, which we're going to construct in some way, which it will become clear in a second. So for us, what is more important is to prevent use of relations between Lorentz generators, which stem from the fact that Lorentz generators can be in a fixed representation. So because of this, we're just going to relax the transversality condition. So our fields will be unconstrained as far as transversality goes. So we can describe them in a more efficient way by going to a two-component spinor notation in the standard way by contracting with the Pauli matrices. So this said, a polarization tensor corresponding to such a field with momentum P is some boost acting on the polarization tensor in the rest frame, here called epsilon 0. And to enforce symmetry, we are going to take these epsilons to be a tensor product of identical two-component spinors. Now, the question is, how do we take the classical limit? In Eutin's talk, we saw a classical limit taken in a spinor helicity, in terms of spinor helicity variables. Here, we're going to take the limit in a different way. We're going to pick such rest frame polarization tensors, which have the feature that they localize the spin in some direction, here called n, as much as it is allowed by quantum mechanics. That means that they minimize the standard deviation of the spin operator. So this kind of states, or spinors, have been known for quite some time. They go by the name of spin coherent states. And they have appeared a number of times in recent past in high energy physics. They are they appear quite often in condensed matter and other fields. So in terms of the coherent states, this is what the rest frame orientation of the spin is. It's xi, sigma I xi, this is ni. And the rest frame spin vector is given by just this. It's oriented along n, and it has a magnitude given by the number of indices that we have. Again, this S is the largest spin. The largest spin that appears inside this field is S, but in principle, there are representations of the little group that go S-1, S-2, all the way down to 0. And in the original formulation, this thing is the last relation was used to project them all out. So with this in hand, we can play a little bit with boost and derive a number of cute relations like these, which are not valid in general. They are valid strictly in the classical limit, and the terms that are being ignored are written here as order Q. This is in the scaling I was describing a few slides ago. So the thing to see is that the product of two polarization vectors is a pretty complicated function of the spins. This has appeared also in Newton-Stock. And also the expectation value of any product of any symmetric product of Lorentz generators can be pulled out from the expectation value in the form of the spin tensor. And the spin tensor is related to the covariant spin vector in this nice way. All right. So this is all about kinematics. What about the actual Lagrangian and the dynamics? What we do want is to covariantize the most general parity symmetric and time reversal symmetric stress tensor, which can lead to long-range interactions. So that stress tensor has been written in terms of form factors a long time ago. And there are 4 such form factors. 2 of them lead to local interactions because they collapse whatever propagator this stress tensor is attached to. So there are really only 2 form factors that can appear, and they are these 2, F1 and F2. And if we keep just the first term in F1 and F2, which is also at Q equals 0, oh yeah, Q is the momentum carried by the graviton. If we keep just the constant term in F1 and F2, this is the action that one might write. This action has been, this phi is one of these fields that I was describing earlier. And because of the construction we are using, it carries only tangent space indices, these spinor indices, which is why everything is written in terms of a spin connection rather than in terms of a Christoffel connection. So that minimal action was analyzed a while ago. And the conclusion was that its scattering amplitudes grow a little bit too fast at high energies. And to tame that growth and restore a remnant of 3-level unitarity, one needs to add such a term, which has the same number of derivatives as the original. So it's not a higher derivative term, which is why we call the action still minimal. They figured, Tensor, Parati, and company, they figured out that to restore unitarity, in this sense, H has to be 1. This is to be contrasted with an H that comes out of string theory, which generates such a term, which gives a slightly different value. This is probably related to the fact that there are many other fields in string theory which contribute to the unitarity condition. So this is the minimal action that one might want to consider. Now, clearly, this does not accommodate the stress tensor. It accommodates at most 3 terms in it. The rest of it can be accommodated by such an action, which has many derivatives and many terms, infinitely many of them. This was modeled on the action of Levy and Steinhoff, the worldline action of Levy and Steinhoff. And that includes the notation for the coefficients, CES and CBS. So I need to explain a little bit what these objects are. The fields phi are the same as in the minimal action. R is the Riemann tensor. These are the standard covariant derivatives, and this volt-phased S is a covariantization of the Pauli-Lubansky tensor operator. All right, to check that this is indeed the action that we should be interested in, all we have to do is extract the stress tensor, which I did not write out explicitly because it's a little long. It's the sum of these 2 terms, which are written in a rather cryptic way. These E hat and B hat are infinite sums with these 3 coefficients, and then use them to compute something that has been computed before. So something that has been computed before would be the 2-to-2 scattering of 2 such things. And using the fancy formula with the comment that I was describing about extracting the Lorentz generator from between 2 polarization tensors, one finds some expression which can be compared with, for example, the stress tensor that Justin Vines showed in his talk this morning, which I'm copying it here. And the comparison shows that, as has been said before in Eaton's talk, CES and CBS come out to be 1. There's a slight degeneracy here. The operator CES2, that is n equals 1, is the same as this H, quadruple coupling operator. Therefore, when we add the non-minimal part of the Lagrangian, we should ignore H, or we should ignore CES2, depending on preferences. I should also say, so this implies that H equals to 1, and therefore it saturates, it agrees with the unitarity constraint that comes from the analysis of scattering amplitudes in the minimal action. I should also say that a Lagrangian of this type describes, for example, the massive gravity of the Ram, Gabadadze, Tolley, and others. And in that case as well, H happens to be 1. Right, so now, as it turns out, this stress tensor that comes out of this from this action has an interesting property. Namely, it is itself it is a double copy. It has a nice square root, and that square root comes from is the electromagnetic current coming out of this action. But since I seem to be running quickly out of time, I will not describe that, but I will just emphasize that this is true. And in fact, one doesn't really need all the infinitely many terms. One can truncate, for example, to the minimal coupling, and this way get the standard double copy of a minimal coupling into this into the 3-point vertex of the minimal Lagrangian, including the H term that comes with this particular coefficient, depending on the 2 spins that were part of the double copy. All right, so this is all about tree level. Now, what about loops? To go to loops, it's in fact useful to have a little bit of a discussion with an eye towards including arbitrary multiples and going to arbitrary high loops, by which I mean in the classical limit, that is to any or computing classical amplitudes to any order in G. So, as you might have noticed, the Lagrangian has arbitrarily many derivatives. Therefore, the vertices contain arbitrarily many derivatives. Therefore, they will lead to high tensor integrals and, in fact, arbitrarily high order tensor integrals. So to do calculations, at least at one loop, IBP is cumbersome. In fact, IBP is always cumbersome. But at one loop, luckily, we have an alternative. It's the massive version of the Ford's formalism, which provides a direct link between unitarity cuts before integral reduction and coefficients of an integral basis. So that's so this is what we are going to use at one loop, even though we are not going to use the most general stress tensor. We're going to just pick a particular bit of it. The second thing to discuss is the relation between Lorentz generators and spin dependence. So as I mentioned, the classical limit gives nice expressions for expectation values of symmetric products of Lorentz generators. The antisymmetric parts can be reduced to symmetric parts by using the Lorentz algebra, and this leads to a reduction in the potential number of spin vectors, just because 2 m's become 1 m under the commutation relations. So this might suggest, as I mentioned a little bit earlier too, that such commutator terms are not relevant in the classical limit. However, at L loops, one has at any number of loops, one has superclassical terms or classically divergent terms, which can compensate for such a reduction. And in fact, at L loops, one has L units of divergence, so to speak. So at L loops, one should keep L up to L commutators. More than L commutators are not relevant, but L of them are important or can be important. All right, the calculation of loop amplitudes is, of course, done via unitarity, and this requires no introduction here. at one loop, what one needs, as has already been mentioned a few times, is the one loop is the 3-level Compton amplitude. And we can compute it up to this action. I should say we are, for the rest of, for the remaining 5 minutes of this talk, I'm going to restrict only to the terms involving one spin for each particle. So this is why all we need is the Compton amplitude coming out of the minimal action. And even for that, we can set h to 0 because that brings 2 spins. So the Compton amplitude, as it turns out, has a very nice feature. Once you compute it, you can see it with a little bit of work. It is itself a double copy. It is the product between a spin S Compton amplitude coming out of the Lagrangian I showed you a little bit earlier, and a spin 0 Compton amplitude. This spin 0 guarantees that there is no H term that's being generated. And this amplitude also has a neat feature that it obeys generalized word identities, meaning that it's transverse with respect to the graviton momenta without requiring that the other graviton polarization tensor is transverse. This makes calculation of unitarity cuts quite easy because it trivializes the physical state projector that needs to be inserted here in the cut. It basically turns each physical state projector into the numerator of the Dedonde gauge propagator. So this said, we compute the cuts, we run the massive version of Ford's formalism, and there are no two ways of saying this. This is the answer. It might look a little bit scary, but it will collapse in a slide or two. There are a couple of things that I want to point out. Of course, I don't expect anybody to follow this, this formula except those who already computed them. So first of all, notice the arrows. If you count the classical counting for spins in Q, you might notice that these are subleading. They're not homogeneous, as I was describing earlier. There are 2 units here, and the third, and then just 2 spins. So this is a subleading term. However, this comes together with a box integral. So it is overall of classical scaling, so it needs to be kept to actually keep things consistent. The other thing to notice is the presence of poles in sigma. Sigma is this variable. And sigma equals to 1 corresponds to the rest frame. So this just means that there are poles in this amplitude at p equals 0. And these poles, in fact, are a consequence of, if you wish, integral reduction, or the massive version of Ford's formalism version of integral reduction. All right, so now how does this compare with things that have been said before? Well, we can take the amplitude and expand it in p equal to 0 limit, and that recovers Pn results computed by Holstein and Ross at finite spin. Again, this is just a single spin of each kind, which is why they agree. And also it recovers Pn results of Chung, Huang, and Kim and Lee. And also we can compare with the spin-a-half amplitude computed by Damgard, Haddad, and Helseth in a heavy particle effective theory. So the comparison is one has to take the product of polarization tensors to be 1 and the expectation value of M to be S. So these are consistent with ours, but they produce a single factor of the spin, and they don't take into account potential subleading terms, which are in fact important if one wants to extract a classical limit. Right, so as a step towards extracting the classical limit, it's useful to expose the rest frame spin vectors. And here they are. In the process of doing that, the result collapses quite a bit. This is the entire amplitude. One still has to expose further spins from the product of polarization tensors, but those have this nice exponential dependence, so we know what they are. Expanding and extracting the spins just reorganizes a little bit the coefficients A1, these A coefficients. Despite being the entire amplitude, it is substantially simpler than a single term in the NNLO post-Newtonian Hamiltonian, that contains S1, S2 type interruptions. That was derived some time ago by these people. So the thing to notice is, like I said, this is pretty simple. And this amplitude is, in fact, the input in the construction of an effective Hamiltonian that could later be used to study bound state problems. And we may hear about that from Chao Shen's talk. And it is also the input in a direct relation between amplitudes and observables in the spirit of Kalin and Porto, and also in the spirit of O'Connell and Kassauer and Maybe's work. So with that, I am at the end of my talk, minus an animation. So I hope I managed to convince you that there is a higher spin Lagrangian that can be used to study interesting problems in GR. And as a demonstration of that, I've described for you a piece of the scattering of two higher spin fields to all orders in velocity, which is also bilinear in spins. And in principle, it can be done to higher orders in spins as well. The future is bright and loud, at least in gravitational waves. The prime application of this formalism is to gravitational wave physics, and there are a number of obvious problems to be discussed, including how to interface this formalism with the one of Kassauer, maybe O'Connell, and Vines. And of course, there are other questions, such as whether it's possible to constrain the coefficients of this higher spin field theory using fundamental properties. And I understand that this is work in progress by other people. So the message is that we should expect new results in the near future as far as spin is concerned and as far as gravitational waves physics are concerned. Thank you.
All right, let's have a virtual round of applause for Radu as we open up the floor to questions that may have occurred to people during the talk. As we wait for those to come in, maybe can we get some sense of, now that you have the formalism set up, Radu, what level of effort is it going to take to extend it to more spins and higher loop orders?
So it depends on your tolerance, really, as always. Including more spins at one loop is not terribly complicated. All one has to do is go back to the Lagrangian and extract the contact term, two higher spins and two gravitons, and then put them in, construct the Compton scattering, and then run Ford's formalism on the result. This can, with sufficient effort, can be done to all orders in the spin, given this particular form of the Lagrangian. At that order, however, one still has to worry about potential nonlinear response functions, or better said, other terms that contain, say, R² type terms. And those, as far as I'm aware of, have not been classified yet. Here we were lucky that Levy and Steinhoff essentially classified all the terms with a single power of the Riemann tensor. But that is definitely something that can be done and perhaps should be done at some point. Yeah, I guess that's a long answer to a simple question. Nima.
Thanks, Radu. As you know very well, there are ancient constraints on Lagrangians for massive higher spin particles, essentially coming from things like superluminality. Like you can't couple massive higher spin particles to general backgrounds, gravitational backgrounds, electromagnetic backgrounds, without having things like superluminality. And those are reflected in the sort of bad properties of the Compton amplitudes from the on-shell point of view. But can you see in this sort of a very nice compact formalism for talking about all such actions at once? Can you see that there's no way of choosing the coefficients to avoid superluminality, or is there some limit as the spin becomes large where somehow it goes away? Are any of those things easier to see in this formalism?
I have not thought about superluminality. I did think about, well, I mean, they are related. I thought a little bit about causality, and
yeah, that's the
they're related.
same thing. Yeah, right.
So,
right.
so in that language, so the classical limit. Okay, so sorry. In that language, the problem, the causality problem, had to do with the fact that one did not, one allowed these particles to get arbitrarily close to each other, right? If one keeps them far apart, such that this classical limit is consistent, such that this the construction of the classical limit is not violated, this one, then in what I could see, there was no real breaking of causality, at least not in, there was no time advance that was appearing. However, that would be a d-dimensional argument. In 4 dimensions, there is an infrared divergence, which I'm sure you know about, which appears at 3 level, which kind of swamps everything, and this argument does not immediately go through. So the short answer is I don't really know. But this is, if my understanding is correct, this is what the people looking into the last item of my conclusions are looking into.
Thank you.
Mm-hmm.
Looks like we have a question from Piswajit.
Yes, so I have a question about one of the point mentioned in the last slide. Like it is mentioned that emission of radiation from the interaction of the spinning bodies can be determined using this kind of action. So my question is that when there will be gravitational radiation, obviously the gravitational radiation also carries spin. So in that case, can you give some insight how one can carry out the calculations to determine the gravitational waveform for spinning black hole scattering problem?
All right, so what can be computed using this formalism is a non-elastic amplitude. So spin 1, spin 2 goes to spin 1, spin 2, and the graviton.
Right.
Right, so there are many steps that go between this amplitude and an actual gravitational waveform, and some of them I have no idea how to take. But definitely what I had in mind with this item on my to-do list is computing amplitudes of this type. Spin 1, spin 2 goes to spin 1, spin 2, and gravitons, 1 or any number. And that's really not a difficult calculation.
Okay, thank you.
Gustav, do you have a question?
Hi, thanks. Thanks for a really nice talk, Radu. I was wondering about the Compton amplitude, which goes into the one loop cuts you were talking about. So, firstly, what exactly it looks like, and maybe if you can say a little bit more about how you got it.
So it's here. This is the Compton amplitude, and in fact, it contains a little bit more than than goes into the calculation. So. It was originally computed straight from the action. So this is the action, extract, where is the minimal action? So it starts out with this, extract the 3-point vertex and the contact term that comes out of here, and just compute the 3 Feynman graphs that go into the Compton amplitude. And once this is done, you need to grab Andres, and he will look at it, and he will tell you, oh, this is a product, and it's a product of these 2 things. So that's how it was computed.
And the contact term?
This is a post factum observation, if you wish. So the contact term is buried somewhere in this product. Right. So notice that the product, of course, just like a KLT relation, it has well. Well, the contact term is in here. Oh, the contact term comes from these factors. Once you push them in, and you know, they can cancel 2 of the 2 propagators that appear in this product. And the pole here is, if you wish, it has to do with the graviton that comes out, and that can also be canceled. Yeah, so the short version is the contact term coming from the action is buried in here somewhere. Does that answer the question?
Yeah, yes, it does. Thank you.
Okay.
Great, and then we have a question from Alfredo.
Hey, yes, thank you. So just to clarify, so in this form of the Compton amplitude, you don't seem to have a 1/m divergence, right?
1/m divergence.
Say the high energy limit, it seems to be healthy.
Okay, it does seem that way, yes.
Right, because this is another way of seeing the problem with causality or superluminality, that all the quantum Compton amplitudes at 4 points, they should have this 1/m divergence, which should somehow be.
So the 1/m, there is no way to generate the 1/m coming out of this
Right. So
minimal action. But in that case, the problem, so there is a unitarity problem in that case, not in the form of 1/m, but in the form of the amplitude growing a little bit too fast, which I can't immediately see it from this expression, but it appears if you keep track of these two terms, if you keep track of the spin square terms, which we really in the end didn't exactly keep track of because we didn't need to for this calculation.
Right. Yeah, I guess we can discuss it later. But I was wondering if this is supposed to be an output of your classical limit, which is somehow built in.
The common.
Yeah, Choshan.
Yeah. So I think here we only have spin 1, spin 2,
Yeah.
the one Radu just showed. So it's in some sense it's like the same as fermion. So that's why you don't have an obvious problem. But if you continue to go on to include higher spin coupling, then of course you'll run into the issue.
Well, surely if you include the higher spin couplings, then you have all these 1/m's which are explicit in here. So
they're all the 1/m's in the Lagrange. Oh, sorry, that's what you just said. Yeah.
Yeah, they're all here. And one might wonder why exactly this is 1/m and not 1 over another scale, but that has to do with the fact that this is supposed to integrate out physics of the object, not some other random physics, which is why these operators are suppressed by the mass of the object rather than by some higher scale.
But I guess if you go to high enough multiples, right, then you will see this problem very explicitly. Yeah.
Yeah, I mean there is this 1/m all over the place.
Yes. So is it that you're dropping the higher multiples, or
so for the formula that I showed you, we did drop them because we really wanted to compute just spin one, the spin of one particle times the spin of the other particle. We had no spin square. So the spin square and higher, they all come with this 1/m's. So
I see. Okay. Yeah. Okay. Thanks.
Mm-hmm.
And then maybe we have one more question from Lance.
Hey, Radu, nice talk. This might be related to the previous question, but I thought there were some versions of the higher spin gravitational Compton amplitude that had poles in spurious locations. And do you not have those because you haven't gone to high enough order in the spin, or because they shouldn't show up in the way you're doing it? If you know what I'm talking about.
I don't know what you're talking about. I was about to invent an answer without knowing the real question.
About this? Can I just make a quick comment?
Go ahead,
about this?
Nina.
Yeah. So of course, there is no spurious pole in the actual amplitude.
Right.
It's just that if you take the formula you get from low spins and dumbly continue to high spins, then you'll get spurious poles. But the fact that there's a spurious pole there is just an indication that the continuation isn't smooth. And you see it in when you do compute the amplitudes that factorize correctly using minimal coupling or any other coupling for that matter, you only have normal poles, but you get inevitably 1/m's downstairs. So that's so the sort of spurious pole is there in the continuation from the sort of familiar results at low spins, and it's just an indication that something new happens when the spin gets to be 5/2 or bigger. And
so he probably shouldn't see that in the way he's building up the amplitudes. Is that correct?
Yeah, you would never see a spurious pole from a Lagrangian ever, of course. You'll only get ordinary poles, but you should see the 1/m's. And
Okay.
I think that the only reason they have not seen the equilibriums is just what we were saying a second ago, that the expressions are for low enough spin where this effect doesn't yet show up.
Let me actually say it differently. We do see 1/m's all over the place at tree level, where we did keep the entire spin dependence, right? So I didn't tell you what these E hats are, but they are all functions of Q dot S over M. So every time you see a Q dot S, you should think of it as Q dot S over M. So they're all here, right? At tree level.
Thanks, Radu and Nima.
Mm-hmm.
All right, with that, let's give Radu another round of applause and thank you.